Okay, welcome students to the next lecture of this series. Last class we talked about radioactivity and we discussed about the Rutherford-Soddy's law of radioactive disintegration. That is, in mathematical form, we wrote it as n is equal to n naught e to the power minus of lambda t. So this equation is about the Rutherford-Soddy's law of radioactive disintegration. And radioactivity, as we understand, we discussed it in the last class. This is the phenomenon in which some substances spontaneously disintegrate, or rather the nuclei of some substances or elements, they are unstable and they spontaneously disintegrate into different forms. They undergo a decay process, emitting particles and radiations. So three kinds of particles and radiations are emitted in the process, as we discussed in the last class. If you remember, we talked about the emission of alpha particles, the beta particles, and the gamma radiation. Then we discussed about these laws of radioactive disintegration, laws of displacement, and the laws of radioactive disintegration. So radioactivity is a phenomenon which will obey certain laws. And this is the mathematical form of the law of radioactive disintegration. This simply states that if I have a radioactive element, I have a lump of radioactive element having certain number of atoms and hence nuclei, the number of radioactive atoms or nuclei for that purpose, it keeps on decreasing exponentially with time. That means the radioactive substance, it decays with time. So this decay, the rate of decay is characterized by, it's a characteristic of the element, it's characterized by the constant lambda, we call it the decay constant. We call it the decay constant, and it is different for different radioactive elements. So simply means that if I have a radioactive substance, the number of atoms will keep on decreasing with time. So this, the number of atoms of a radioactive substance or element at any instant of time t is given by n, that is equal to n naught e to the power minus lambda t, where n naught is the initial number of atoms present. So with time, the number of atoms, it keeps on decreasing. So as I told you, this decay is characteristic of the element. So if we want to compare the rate of decay of different radioactive elements, the parameter that we have in our hands is the radioactive decay constant. Also, we have to talk about some time here. So one time that we are defining here is the half-life. It's the half-life of a radioactive substance. So what it basically means is that the half-life of a radioactive substance can be defined as the time in which the number of atoms of the radioactive substance decreases by half. Simply means, let us say that we start our clock, we start measuring time at an instant of time t is equal to 0. When we start our clock, this is the time t is equal to 0. Let us say the number of atoms of the radioactive substance at that instant is equal to m naught. So with time, the number of atoms will keep on decreasing exponentially. So this is time along this axis. Initially, this is time is t is equal to 0. We start with m naught. So with time, the number of atoms will keep on reducing. And it takes infinite time to go to 0. We talked about it in the last class. So this is m naught. So let us say this is m naught by 2. The number of atoms reducing to half that was there initially at time t is equal to 0. So this time we can call it this instant of time t is equal to t subscript half. We call it t half. The amount of time, the length of time in which the number of atoms of the radioactive substance reduces to half its initial value is known as the half-life of the radioactive substance. So this half-life is of course related to the rate at which the element disintegrates. So this half-life of a radioactive substance is dependent on the disintegration constant. So now we have to find out a mathematical expression for this. So let's see how we can do that.